Have you ever wondered how your phone, laptop, or even your smartphone control electricity so precisely? Today, let's explore the field effect transistor, or FET, one of the most important electronic components.
FETs act like a water flow spigot that is open all the time unless you are actively closing it. In this analogy, a negative gate to the source voltage closes the tap, while the drain to the source voltage is the water pressure with no voltage on the gate. If there is water pressure, water will flow.
Now, let's see the working principle. When you apply a voltage to the gate, it charges up like a plate in a capacitor. This electric field attracts or repels electrons in the channel between the source and drain. If enough electrons gather a conducting channel from current flow, if the field pushes electrons away, the channel shrinks, current stop. So the FET acts like a voltage control switch. Gate voltage high, channel on, current flow. Gate voltage low, channel off, and current block. A field effect transistor, FET, function the same way as a mechanical switch. They both control the opening and closing of the circuit. The two main terminals of FET are equivalent to the tool contact of mechanical switch. Like the button of a mechanical switch used to control the on-off state. The difference is that a FET is controlled by a voltage. When we apply a 3 volt voltage to the gate, the light turns on. Even after the voltage is removed, the FET remains the on state. This happens because of the internal structure of the gate is similar to a capacitor. It holds the charge and keeps the FET conducting. To turn the light off, a reverse voltage must be applied to the gate.
There are two main types: junction field effect transistor and metal oxide semiconductor field effect transistor. JFET has 3 terminals: gate, drain, and source. The gate is a reverse biased PN junction that controls the channel conductivity. The junction field effect transistor, JFET, controls current flow between the source and drain terminals by adjusting the voltage applied to the gate. This gate voltage creates an electric field that varies the width of the depletion region in the channel, effectively acting as a voltage-controlled variable resistor to regulate current. The junction field effect transistor, JFET, controls its internal current flow, conductivity, by changing the size of the depletion region. This control is governed by a mathematical formula that relates the actual current flowing to the device's maximum current capacity and how close the gate voltage is to the voltage needed to shut the device off. Second type is MOSFET. It is a 4-terminal component: gate, drain, source, and substrate. 1. Its gate is separated from the channel by a thin layer of silicon dioxide insulator. 2. This isolation results in an extremely high input impedance 3 and means MOSFETs require almost no input current to regulate the load current, unlike bipolar transistors. 4. The linear model is typically used for switching applications, digital signals and analog multiplication. The drain current equation is given as below.
Field effect transistor is essentially a switch, but instead of moving parts, it uses semiconductor physics to control electricity. So now we are going to take a look into the part of the FET. Normally, current cannot flow from source to drain because the p-type body between them acts as a wall. It begins with the substrate, a single crystal of silicon. We dope this with boron to make it p-type, meaning it has positive charge carriers. Inside this base, we create 2 reservoirs, the source and the drain. These are chemically altered to be n-type, meaning they are rich in electrons. To solve this, we place the gate on top. Crucially, the gate is protected from the silicon by a super thin insulating layer of silicon dioxide. This ensures the gate never physically touches the channel. When we apply a positive voltage to the gate, it creates an electric field that penetrates the glass. This field attracts loose electrons from the substrate and pulls them to the surface. The inversion layer, these electrons pile up and form a contemporary conductive bridge called F inversion layer. This physically transforms the surface of the p-type silicon into n-type. Suddenly, the wall is gone. The source and drain are connected and currents flow freely. When you remove the voltage, the electrons scatter, the bridge dissolves, and the switch turns off. We built this structure using the planar process. We use photography to print patterns with light and ion implantation to bombard the silicon with atoms, creating the doped regions. This result is precise atomic-level switch that can operate billions of times.
Field effect transistors are widely used as amplifiers in electronic circuits. Because FETs have high input impedance and low noise characteristics, they are ideal for boosting weak signals. You can find FET amplifiers in voltage amplifiers, buffer amplifiers, sensors, and low noise amplifiers, LNA. Their stable and linear response makes them essential for achieving clean, high-quality signal amplification. FETs are also used as electronic switches. A small voltage at the gate can turn the device on or off, allowing precise digital switching. This makes FETs the backbone of logic circuits, microprocessors, and memory chips. They provide fast switching speed, low power consumption, and high efficiency. In some circuits, FETs act as voltage-controlled resistors. By adjusting the gate voltage, the channel resistance changes smoothly. This function is commonly used in analog circuits such as electronic dimers, audio mixers, AGC, automatic gain control systems. FETs provide precise control with excellent stability, making them useful in many analog applications.